Okay, let's get started. We've just come out of the first section of the course dealing with the core theory, the theory of externalities. We talked about the fact that externalities exist. There's activities in the market, transactions between willing buyers and willing sellers, which result in negative effects on third parties. Those are called externalities. And we talked about different approaches or different philosophies for how to deal with those. In one case, just assigning property rights to one party or the other in terms of who has the right to do some activity or who has the right to be free of harm from that activity. Assigning those rights, if conditions are right, assigning those rights properly will lead to an efficient solution through just negotiation between those parties. That was the Coase theorem, the idea that if transactions costs are low and property rights are well defined, the people involved in the externality, the one being harmed by it and the one perpetrating it, those parties will have an opportunity and an incentive to reach a mutually agreeable solution when transactions costs are low. That's one kind of way of approaching the problem. And then we also mentioned how it can sometimes be impossible for negotiations to occur between it can be impossible for negotiations to happen over certain kinds of externalities, especially where there are large numbers of parties involved and there's incentives for free riding and holding out, and maybe if there's not a strong social cohesion among the members of that group, it can be difficult for any kind of bargaining to take place. So we also mentioned how there's another way of coordinating behavior. It would be to put on a Pigouvian tax on the activity that's harming third parties, and so that we showed how slapping on that Pigouvian tax changes the incentives of suppliers. It sort of implicitly raises their costs, and it causes them to shift. We end up shifting from maybe the unrestricted market quantity QM. We go from QM to something a little bit smaller under that tax, which would be hopefully Q star. If we set the tax at the right level, we get to Q star. Q star is where we want to go. That's the place where social marginal cost equals marginal benefit. And if we set a tax which gets us to Q star, so setting a Pigouvian tax which gets us to Q star, that's called internalizing the externality. The externality was previously outside of the transaction. It was not being accounted for. Putting the Pigouvian tax on that activity, quote, internalizes it. It brings it inside the market, and now suppliers and consumers have an incentive to take into account those external costs. And as they respond to that Pigouvian tax, in principle, they're going to reduce their quantity to Q star if the tax is set at the right level. So that's kind of where we've come out. We've have the approach of assigning property rights, which can be very effective because the parties involved directly have a stake in what's going on, and they have the most information about possible remedies and what the benefits and costs are in that situation. Other cases, something much more on a larger scale might be more appropriate, like a Pigouvian tax, when it would be too difficult for individual parties to come to a mutually beneficial agreement. That's a little bit of review of where we've come, or from where we've come. We're going to move into next this topic of common property resources and public goods. Okay, so as we think about sort of public goods or common property resources, there's two characteristics that matter for how those goods are treated economically. So we have these two properties, excludability and rivalry. Those are two dimensions of a good which matter for how that good gets managed. Rivalry has to do with whether or not you consuming the good diminishes the quality for other people. So we'll get to some examples, but just keep that definition in mind. Rivalry is when your consumption of something means that there's less there for somebody else. In the case of the contributions into the public good in the game we played, those were not rival. Those were non-rival because it didn't really matter like how many players there were. Everybody was able to collect the average contribution times two. And if we had added, 30 more players, that still would have been true. You would have been able to collect the average contribution times two. It didn't get diluted in that way. So that's one dimension is the rivalry. The other dimension is the excludability. So a good is non-excludable if you can't prevent other people from enjoying it or using it. Again, this is the case with those contributions to the public good that you made in the game. So you contributing to the public good. You had no way of preventing other people from collecting that. Collecting the average amount times two. You couldn't prevent other people from collecting that, regardless of whether you contributed or not. You were able to collect that amount. So that was non-excludable. So those points were non-rival, and they were also non-excludable. We can think about different resources or different goods having different degrees of excludability and rivalry. I have a diagram here which illustrates this. You have these two dimensions of rivalry and excludability. Down here in the bottom left-hand corner, you have goods that are both rival and excludable. So these are things like private goods, like your laptop computer, your house, your shoes. You have a legal right to exclude other people from using those things. And if you're using your car or you're using your computer, you can't have someone else use it at the same time. It's rival in that way. There's other goods. So like like a toll road, that's a good in which it's excludable because you have to pay in order to get on. There's a gate that prevents you from entering the toll road. But you going on the toll road doesn't really prevent other people from going on the toll road, except to the extent that you increase the congestion a small amount when you go on the road. So this is located kind of in the middle of this rivalry axis because of the fact that there's possibilities for traffic congestion. And so when there's congestion, when there's traffic congestion, it's not complete rivalry, but you are diminishing the quality of the road a little bit for other people by having your presence on the road because you are contributing a little bit more to the congestion of traffic. Okay. Something like, private Wi-Fi. Again, that's something that you have to have the password. You have to have the subscription to have access to that Wi-Fi. And it's a little bit rival because if you have a lot of people on the private Wi-Fi, even if you're all pitching in and paying for it and you have access to it, too many people on the Wi-Fi can make it slow down, and in that case, it gets to be a little bit rival. Cable TV would be an example of something that's non-rival, but it is excludable. So you have to subscribe to get cable TV. But if you have cable TV and you're watching cable TV, you're not like eating up the cable TV and making there be less cable TV for other people. You're able to enjoy it, and anyone else is able to enjoy the same programming because it doesn't get consumed when you use it. Kind of some other examples that with going back to the Wi-Fi and the roads, a freeway or a public Wi-Fi, that would be something where you have non-excludable property. So you're able to just go on the freeway without having to put money in or have an iPass or something to get through the gate. Same thing with public Wi-Fi. You don't have to have a password, but you do have both of those things have the opportunity to be congested if there's too many people using it. So there's some degree of rivalry. It's not complete rivalry, but there's some extent to which your presence on the network diminishes the quality for other people by a small amount. And then up here in the upper right, you have what's pure public goods. Those are things that have neither excludability nor rivalry. So national defense, the fact that the United States spends a certain amount on their military, you are able to benefit from that, and the fact that you're able to benefit from that doesn't prevent me from benefiting from that as well. We all kind of share the benefits of having a defense against enemy invaders. Public radio is another example. You can't. It's broadcast over the airwaves, so you can just tune in and listen to it. It's not excludable that way. And also, if you listen to NPR, I can also listen to NPR, and your quality is not affected at all. So it's helpful to have this diagram in your head, and to think about where different kinds of resources fit along these two dimensions of excludability and rivalry. So we are going to, in this next part, we're going to talk about fisheries as being an important example of common property resources. So these are fisheries, other kinds of natural resources which are available for extraction. Those fall into the category of common property resources. Things which are rival, where your use of that good or your extraction of the good leaves less for other people, but there's no mechanism for preventing the use of it by somebody else. There's no fence. There's no fence around the ocean. At least there's no fence around the open ocean. That's kind of, there's some extent to which countries have jurisdiction within like 200 miles off their shore, but beyond that, it's the open ocean isn't owned by anybody, and there's no national government that has jurisdiction over the open ocean. And so in that case, there's no way to fence off the ocean and prevent people from fishing in it. So that's non-excludable. But if you are extracting resources from the ocean, you are diminishing the amount that's available for other people to extract. So there's rivalry, but not direct excludability. In a legal context, we say this is subject to the rule of capture, which was just part of English common law, saying that if you are the first person to put something to beneficial use, to either withdraw the groundwater from the aquifer, or catch the fish, or hunt the antelope or something like that, you're the ones who, after you do that, you own the good. That's the rule. The rule of capture says the first person to take it is the one that owns it. And so that applies to this fishery case, but it also applies to things like groundwater and oil and wildlife. So we're going to look at this case of the fishery and look at some of the economic characteristics of the fishery. So we're gonna make some assumptions, and just look at a very simple, stylized case of an open access fishery, making a lot of simplifying assumptions, just so that we can get the concept of what's going on with how to, like, what breaks down, how do the incentives in an open access fishery break down, how would we like the incentives to be, and what could we do in order to steer incentives more towards something that would be overall more productive. So if you have a fishery, one of the things that one important characteristic of that fishery is that it gets easier to fish the more fish that there are. The higher the fish stock is, you don't have to search as far and wide in order to catch fish. You have a lot of fish available. You can cast your net, and you're more likely to get a good return of fish when there's an abundant stock of fish. So fishing, that's going to be a key point in the economics, in the economic analysis of the fishery, is that fishing effort is going to the amount of fishing effort you have to expend is going to depend on the stock of fish. So when the fish stock is large, it's very easy to to get a high return with little time or little effort, and that affects your economic costs, right? As the number of boats increase, however, that stock of fish is going to decline, and as soon as you start to get the stock declining, it just becomes harder to find the next fish. Each additional fish gets harder to find as the total stock falls because they're not as abundant. You're not as likely to just get a fish right there when you cast your net over the side of the boat. So there's a in some ways that's kind of like the congestion effect that we saw before with roads and Wi-Fi, where the more people you have using it, the stock gets diminished, and that requires that you put forward more effort in order to catch a fish, or for a given amount of effort, it means you have a lower return. Okay, and then in the long run, it's possible for actually the total production to actually go down because you've damaged the capacity of the fishery to replenish itself. You've overharvested and put some strains on the fishery. It's actually really hard to completely exhaust a fishery because, again, catching the very last fish is very hard to do. If you're going to try to catch the very last fish, it would take you a lot of resources to track it down and catch it because it would be so hard to find. But you can diminish the stock to a very small level so that it's as if you've caused it to, for practical purposes, go down to zero. So keep those things in mind. The fact that the cost of fishing or the return on fishing falls as the fish stock falls. That's going to be an important economic concept that will play into the optimal management of the fishery. So that relationship is given here by this graph. So this is what I just described, how you have this relationship here where we're increasing the number of boats. So let me just point out that number of boats here is on the x-axis, and the total fish catch is on the y-axis. We're going to use the number of boats as a proxy variable for fishing effort. We're just going to assume, again, this is a stylized example just intended to illustrate the key economic points. But we're just going to assume that a single boat has a certain amount of fish that it can catch, and fishing effort is going to be represented by increasing the number of boats. So as you increase the number of boats, the return goes up at a constant level initially because each additional boat is able to catch the same number of additional fish. And that occurs for a while. When the fish stock is large, that's true. Each additional boat catches the same number of additional fish. But then you start to get that congestion effect where you reduce the fish stock, and a given amount of fishing effort doesn't return as many fish because the fish are sparser. It's harder to find them. So your return continues to increase, but it starts to level off in that middle section of the graph. That's where it gets harder to find the fish. And then after a while, you get to a point where you're actually starting to fish to such an extent that you're reducing the capacity of the fishery to replenish itself, and you're actually getting less total output even as you're adding more boats to the fishery. So let me just point out, already we can see there's something wrong with this part here, because that's the total amount of fish you can catch, like for not an individual, but that's the total amount of fish for the entire collection of boats. And so this cannot possibly be the most efficient level of fishing effort, because you could put in less effort. Let's say you're out here at, in the 1200s of boats, your total catch is close to 50, I guess close to 5,000 tons. Is that, this is in hundreds of tons, so that's about 5,000 tons with this 1200 boats. If you reduce the number of boats, you lower your costs, right? So you have fewer boats, you're spending fewer resources on fishing, and you're getting more out of it, right? So it's not even that the catch per, I mean, the catch per boat is definitely going down, but certainly like it's even the case that the total catch is going down. So immediately we can say this cannot possibly be a good economic outcome or a good outcome for the fishery, because you have a possibility of increasing the total catch by spending less resources. So that's a no-brainer. You definitely not want to be out there. But we're going to see in a second, there's actually nothing stopping people from individually going out to this point for kind of the same reasons as we saw in that public goods game. There's personal gains to be had. Like an individual boater doesn't care about the total catch of the fishery; they care about their own personal catch. And we're going to see in this example, we're going to see that individual people actually naturally, if you leave them to themselves, individual fishermen would naturally fish to this level way out here, because of the personal gains to themselves. So let's put some numbers on this and look at this a little more closely. This is what I just said. This is just the different phases of production that are exemplified by that graph. Initially, you just have the fishing technology is what's limiting you. The stock of fish is abundant, and it's only the technology in the boat that's limiting the amount of catch. And then in that next phase, the middle phase, you have the stock of fish becomes scarcer, and that's actually the thing that starts to prevent the catch from being higher. And then, as we saw way out on the right, you get to the point where you're starting to reduce the capacity of the fishery to replenish itself, and potentially having some long run consequences on the fishery. So those are the three phases that were illustrated on the previous diagram. That previous diagram was total fish catch in tons or hundreds of tons. So let's put some monetary values on this, and we can combine that with some monetary values of the amount of the costs, and we can start to evaluate the situation from an economic point of view. So this first row is the number of boats. That was the x-axis of the previous graph. The total catch is in the second row. That was the y-axis of that previous graph. So these numbers in the first two rows are just simply this graph here. So you'll notice that the total fish catch goes up from 10 to 20 to 30 to 40 to 48. So from 40 to 48, we already see that's where the returns start to diminish a little bit, where you no longer have the same increment of total catch as you add the next 100 boats. So the total catch starts to go up, but at a decreasing rate. Eventually it levels off around 6,000 tons here. This is 100 tons. These are in units of hundreds of tons. It levels off at 60, and then it reduces down from there as you add more boats. That's the absolutely diminishing returns that we saw before. So one of the assumptions we're going to make is that the total catch, so the total catch, which is represented by this second row of the table, the total catch is going to be spread equally among all the fishermen. So again, this is just a simplifying assumption, so we can just focus on the crucial economic concepts that we're trying to learn. We're going to assume that the total catch is spread equally among all the boats. So no individual fisher is any better than any other. They all have the same fishing technology, and so they're all kind of just sharing identically in all the gains. So if you take the number of boats and if you take the number of tons and divide that by the number of boats, for example, you can find here that on the left you have 100 boats with 1,000 tons of fish for the total catch, and so that comes to 10 tons per boat. And then way over on the right, as you know, you can do that for each of these columns, but you'll notice here on the right that you have 1,200 boats and 4,800 tons, which comes to four tons per boat. So the total catch per boat is going from 10 tons per boat to all the way to 4 tons per boat as we start to exhaust the fish resources. So the economic variables that are going to be important here are we're going to assume that the price of fish is $1,000 per ton. So that just lets us convert the tons of fish caught into dollars. And then we can compare those dollars to the dollar costs of fishing, and that will give us some criteria for evaluating the economic outcomes under different policy regimes. So the price of fish is $1,000 per ton. The cost of fishing, we're just going to assume, again, this is a very simplified example, but let's say that launching an additional boat, the marginal cost of doing that is $4,000 per boat. So you can think of that as being like the maintenance costs on the boat, the fuel costs for the boat, the time costs, the labor costs of the fishermen. It's their opportunity cost. So if they're not fishing, they could be using their time doing something else. So let's assume that this $4,000 per boat includes, the maintenance and the fuel costs, as well as the opportunity costs of their time. So again, let's just assume that each additional boat has a constant marginal cost of $4,000 per boat. Okay, so we have some metric now for measuring the return. We know the total catch and we know the price, so we have some idea of the dollar return to fishing. We have some idea of the cost of fishing. We have this constant marginal cost of fishing. So these next 3 columns are those monetary values. So those are each of these columns in rows 3 through 5 are the monetary returns or costs or profits. Those are the monetary values of the number of boats and the total fish catch that are in the top 2 rows. So revenues go up in exactly the same shape as total catch because it's a constant price per unit of fish. So those revenues are going to have the same pattern of increasing initially, but then decreasing as you add more boats. Costs are going to, remember, marginal costs are constant. So marginal costs are just going to be increasing at a constant level as you add more boats. So if this axis is the number of boats, costs can be represented by just a constant increasing, a line increasing with a constant slope. And then the profit is the difference between those two. So total costs is the curved line. Sorry, total revenues is the curved line. Total costs is the straight line. And so if you think about profits is going to be the difference. And so ideally you'd want to find the point at which you have the largest spread between total revenue and total cost. That is, if you were trying to get the most value out of this fishery, that is the way that you'd go about doing so, is driving the gap between total revenue and total cost as wide as you possibly can. Okay, so that's given, all that stuff is sort of given by this graph here. So again, total revenue is this blue line on top that's curved. It has the same shape as total production. Total cost is a straight line as based on the fact that we have constant marginal costs. And then profits are just total revenue minus total cost. So it's just the black line, subtracting the black line from the blue line, subtracting the gray line from the blue line gives you the black line, which is total profits. And as you can see, those sort of peak around this 650 boat range roughly. That's where the gap between total revenue and total cost is highest. So if we wanted to maximize the total value of the fishery, that's where we would want to be. So it's important to have an idea when you're thinking about policy in general. You want to think about what's the ideal
scenario, what would be like things to be like if we could have them be any way we wanted to? So this is kind of our target. We'd love to have some number of boats between 600 and 700. That would be the number of boats that would give us an ability to capture some of the value of the fish and also allow the fish to regenerate over time and allow the stock to be abundant enough where we're not having super high fishing costs because we have enough fish that it's easy to find the next fish. Okay. The principle that's at work in finding that maximum, the profit maximizing point or the value maximizing point for that fishery is the point at which the marginal revenue is equal to the marginal cost. And so we have a constant example or a constant marginal cost in our example at $4,000 per boat. So marginal cost isn't changing. What is changing though is the marginal revenue. And the marginal revenue isn't changing because of the price. The price is constant, but what is changing is the catch. So that's the key point is the benefits of fishing or the revenues of fishing depend heavily on the existing stock and the existing level of fishing effort. And so you diminish those revenues as you fish more and more. And so there's going to be some point at which the marginal revenues start to fall below the marginal cost, and it stops making sense to continue fishing. And that's the point. That's kind of the point where we saw on that profit maximizing level where we have, the total profits peaking, somewhere, I don't know, around here. That's going to be the point at which marginal cost equal marginal revenue or marginal benefit. Those two terms will be synonyms for our purposes here. Okay. Now let's think about what an individual boat is going to want to do. So this is where we get the dilemma. This is precisely the source of the dilemma. As we increase the number of boats, our fish catch goes up, so the revenue goes up. We can take that fish catch and convert that to dollars, and so this second column is implicitly converting that fish catch from tons of fish into revenue. So initially you have a constant increase. You have these revenues going up at a constant rate. So the revenue per boat, each additional boat for the first 400 boats is able to get the same revenue because they're not generating any congestion. They're not competing with one another very seriously yet. They still have an abundant fish stock, and each boat is still able to catch 10 tons of fish and collect $10,000 of revenue per boat. And then as these diminishing returns start to set in, the revenue per boat starts to fall because you have a declining fish catch, which is starting to be spread over a larger and larger number of boats. So the revenue per boat is going to start falling. So it goes from 10,000 per boat down to 9.6, down to 9, down to 8.2, 7.5, 6.6, 5.8, 4.9. It's going to continue falling as the number of boats goes up, because again, that declining fish stock is being spread over a larger number of boats. The cost per boat is still constant, so we still have a constant marginal cost. Each additional boat costs the owner of that boat $4,000 in terms of the fuel, the maintenance, the opportunity cost of their time. They still have to expend $4,000 for that fishing trip or that level of fishing effort. And that's constant for every boat. Additional boats don't have increasing costs under these assumptions. And so you have, up until 11,000 boats, you still have $4,900 of profit per boat. You still have $4,000 of cost per boat, and so you have a profit of $900 for the 1100th boat, and then you can imagine that kind of diminishing even more as you go from 1100 to 1200. But then it's not until you get to 1200 boats that the profit actually disappears. So it's at 1200 boats where the revenue per boat
just falls enough to meet the cost per boat, and that's where profit is zero. And so individual boats still have an ability to make some kind of profit. They're able to cover their fuel and maintenance costs, as well as the opportunity cost of their time. They're able to cover those costs right up until the 1200th boat. And it's only until the 1200th boat goes out that the fish stock is depleted to an extent, to such an extent that there's no longer positive profits to be had by the next boat. And so you still have an incentive for an individual fisherman to go out and fish up until the point where there's 1200 boats. And that's if you remember from a few slides ago, that's exactly what we don't want to do. That's too much, right? Total revenue could go up if we could have an agreement that we reduce the number of fish, or number of boats that get launched. So that's where the incentives break down. We'll kind of recap this a little bit more next time and talk about some of the possible remedies for this. I'll take any questions on this if you have some questions between now and then. I'm happy to explain some of this again next class, but